temperature. All that gives you, you don't want to know all that because you're not that much into that, I know. Gravitational pressures involved. You need all of this stuff to get gravitational pressure. Gravitational constant, the average mass of the nucleons. You need the mass of the electrons, of course. The effective ion radii for each of those nuclides, which you can determine by calculation. The area, the ion sphere radius for all the ions in the plasma, and then all of that put into this equation, you can arrive at the gravitational pressure. And then the properties that affect the nuclides are the gravitational pressure and the thermal pressure. You put those two things together and you get the magnetic pressure. It's the difference between the gravitational and the thermal pressure. You get the magnetic pressure. From the magnetic pressure, we relate the field strength. This is the magnetic field strength, the magnetic pressure times 8 pi, the square root of that gives us the magnetic field strength. And the magnetic energy is derived from that magnetic pressure and from the volume of the individual components. Okay? So we're looking at magnetic energy affecting each individual nucleus. Okay? And that's how you get it, right there. All right? Simple volume equation. 4/3 r cubed, where r is the radius of the nucleus, and multiply that times the magnetic pressure, you get the magnetic energy. Okay? So there's a radius. It's very small, 10 to the minus 13 meters, the effective nuclide radius. So the magnetic energy per nuclide then is calculated to be from this equation like that in joules. That's converted to MeV. So it's about 5.3, 5 1/3 million electron volts for each individual particle. Now, what did they say? If you have enough energy at each individual particle, will it affect the decay rate? You bet. It's going to affect the decay rate phenomenally. Now, in the end of these 3 days, or actually roughly less than 3 days, we're going to have a cooling off of that plasma, and that's demonstrating this. It's not so bright and orange anymore. It's getting gray. So the Earth is solidifying and being formed. And here's some of the elements, the major elements in the Earth: oxygen, silicon, aluminum, iron, calcium, sodium, magnesium, potassium. And these are their amounts, okay, that we know. These are the total energies. These are the energies to remove those electrons. And why do I need that? Because I have to know what the charges are. That's all. I'm just telling you. Just showing you that because I need to know what the charges are. These are equations that allow you to evaluate the electrostatic effect. That's the charge that you need from those atoms. You put that in here, you can calculate the electrostatic energy. Electrostatic effects, also repulsive effects as well. That's these charges here, Zi, Zj. You need that. You need this constant K. That's an ionic strength constant. You don't need to know all that unless you're really into it. That's the equation you need to do that. What are the results? All total energies, magnetic energy, the electrostatic energy, the energy of the interactions, and the thermal energy. Okay? Those are the energies. You add them up, these are the quantities, and you get a total balance of almost, not quite 0, 0.09 MeVs negative. In other words, if you had a total energy balance from all of those things, it should be ideally 0. Okay? Now remember, we don't have an ideal situation here. We have a dynamic plasma, and I'm treating it as if what? As if it were frozen. So that's one of the errors, but it's close to being balanced. Okay, that's what I want to show you. Those total energies are close to being balanced. The negative energies are absorbed, the positive energies are released. Okay? But that would amount to a plasma frequency of the right order of magnitude, having that amount of energy. See, these two go together. Okay. The magnetic energy is a dominant factor. That's the bottom line. The precise manner as to how that happens, you have to treat each nucleus independently. Okay? And I'm not going to go into the details of that because you really get lost. But you have to treat that independently, and it has been done in the paper. And the increase to the decay rate, the acceleration of the rates, and reducing the half-life, is an enormous amount. And you can see how enormous it is right here. Now this used to be a nice straight table. Before it got put into the PowerPoint, it got all crooked. But you can't hardly read the red numbers anymore. And that's the one I really want you to see. Because these numbers are the numbers for uranium, 238, 235, thorium, 232, samarium, 147, rubidium, 87, potassium, 40. Well, see, the normal half-lives is this column right here. That's in billions of years, okay? That's the billions of years. These red numbers, which are kind of hard to see on that dark background, these are in minutes. 2 minutes, 13 minutes, 16 minutes, 1.6 minutes, 2.5 minutes, 5.9 minutes. What does that say? These billions of years of half-life here have been converted to minutes of half-life when they were in the environment of the plasma. What happened? All the radioactive decay went on like that. It went on very fast within minutes. Most of all the decay that ever happened